Hello everyone, welcome in again to another video session. Today we are taking up the topics of acid-base chemistry, and in particular we're starting with acid-base dissociation constants, which is what we were covering in our most recent class lecture. So just to sort of overlap from where we left off and what we're about to spring into, I want to remind you that an acid dissociation constant, otherwise labeled as a Ka, Ks are universally the way we designate equilibrium constants with a capital K. The subscript A means we're referring to the equilibrium constant of an acid, right? So acid dissociation constants describe the reactions of acids with water. So for example, here we have HClO with water producing H3O plus and then the hypochlorite ion, which would be the conjugate base of our acid. So the dissociation constant would be just like any equilibrium constant. We would put the product concentrations in the numerator, raising them to their respective coefficients, which are both ones in this case, and divide by the reactant concentrations in the denominator, again raising them to their respective coefficients as exponents. Here we've ignored water and not included it because, although I didn't write it, water would be a liquid. The other phases would all be aqueous and therefore included in the equilibrium constant. So it'll be universally true that when you write the reaction of an acid and thus its Ka value or Ka expression, you will always have H3O as part of the reaction, and therefore H3O should always be in your equilibrium constant expression. On the other hand, for anything that is a base, the base reaction, so here I used the conjugate base, ClO minus. What if it was reacting with water? It would produce OH minus and HClO, now the conjugate acid of the base. So the Kb equilibrium constant again features the numerator, the products raised to each in the case of 1, in this case the coefficients, divided by the reactant concentration also raised to 1, its coefficient. We see a lot of ones in these acid-base reactions, as I mentioned earlier in our last class. That's because we're always limiting the transfer of one hydrogen or one proton at a time. So that's going to be a nice perk or benefit of our acid-base chemistry, is that we'll have lots of ones and we won't have those higher power exponents, squares and cubes in these equilibrium constant expressions. So a Kb, a base reaction, to counter an acid reaction, whereas acids always have H3O, and that shows up in their Ka expression, bases always produce OH minus in their reactions, and that should also always show up in their equilibrium constant expressions. So many acids, we know the value, the numerical value of their Ka and Kb. And those are contained on a chart or tables that you might look up. But I've provided for you a resource, a nice summary of probably 30 or so acids that are really commonly used in chemistry. So if you have this Ka-Kb chart, or acid and base ionization constants, another name for dissociation constants, all right? You might want to get it out right now. I'll talk a little bit about this chart. You're going to use it a lot for your work in the remainder of this chapter. So first of all, the chart is organized sort of vertically in two halves. If you were to fold your chart, your paper in half, the left half, as you're looking at it, would be all acids. And then the right half would be all the bases. Okay? So on the acid side, the acids are ranked from the strongest acids at the top to the weakest acids at the bottom, all right, in order. So it's sort of a ranking of what are our strongest species and what are our weakest species. You might notice that the strongest acids at the top don't even provide a number for the Ka. They just say large. Remember that means this system so much favors the product side that we essentially think of it as a complete reaction. It's not even worth thinking about how much of that acid might be left over in the case of one of those acids at the very top of the chart. Okay? On the other hand, at the very bottom of the chart are some acids that are listed as having a very small Ka. If you don't have a number for it, it means you're not going to be able to solve. It's so small that you're not going to be able to solve for what's happening in the reaction. And this would be one of the few cases where we would say no reaction occurs. Otherwise, a lot of our equilibrium constants fall in a similar range to some of the KEQs that we saw in chapter 13, our first chapter on equilibrium. We'll see some 10 to the negative 3s, 10 to the negative 6s, 10 to the negative 11 for that matter. So when we talk about what's a strong and what's a weak acid or a base, generally speaking, we consider anything to be strong if its Ka is roughly greater than or equal to 10 to the negative 2. Definitely anything that has the word large as its Ka is a strong acid, but there are a couple of others that would qualify. And then we consider acids that are weak or to be weak when their Kas start to get to be smaller than 10 to the negative 4. So that does leave a little bit of middle ground there. There are a few acids that are moderate, we might say. The smaller the Ka gets, the weaker the acid becomes. We could flip that around and start to talk about bases. Now on the other side of our Ka-Kb chart, the right side, the bases are organized in reverse order. The bottom of the list is where the strongest bases appear, and then as you come up the list, the bases are getting weaker and weaker. So you see the large is down at the bottom for these, and the very small Kb is up at the top of the list now. All right? So why these are organized in reverse order is because of now the connection across any one row on the chart. If you pick any acid and read across, you see its name, its formula, its Ka, and then next to that is another formula of its conjugate base. And so we see, for example, HClO and ClO minus, which are a conjugate pair, we see them listed side by side on our Ka-Kb chart. It's right here about 2/3 of the way down our list of acids, I would say. We see Ka 2.9 times 10 to the minus 8, and then ClO has a Kb of 3.4 times 10 to the minus 7. So on the one hand, this is handy because it will always show you the conjugate partner of an acid or a base. So you'll have those right there, which is a skill we worked on earlier in this chapter, predicting what the conjugate acid or base is. But now you have all of them listed right there. The other real reason they're listed that way, though, is because there is a connection between the Ka of any acid and the Kb of its conjugate base. If we look at these two expressions, we notice that the two reactions up here they both involve water, and then they both involve the HClO and the ClO minus, although on different sides of the reaction. So there seems to be something similar about them, right? But also something a little bit different. So somewhere along the line, somebody said, what happens if we multiply the Ka of one acid times the Kb expression of the conjugate base? In this case, the H3O plus times the ClO minus for the Ka divided by the HClO multiplied by the Kb expression OH minus times HClO divided by ClO minus. When we have an expression like this multiplied, we can use algebra to simplify. Here we have an HClO in the denominator and in the numerator. We have a ClO minus in the numerator and the denominator. And that's going to simplify this whole expression to just H3O plus times OH minus. We've seen that before. H3O plus times OH minus is the product of water reacting with itself. That's the water ionization constant. So if we read from the far left to the right, we see that for an acid-base pair, the Ka times the Kb equals Kw. In other words, just like for H3O and OH minus, this is expressing an inverse relation between the two partners. A very strong acid will have a very weak conjugate base. which is why then the strongest acids are listed at the top of our Ka chart and the weakest bases are listed at the top of our Ka chart. Right? So the Ka chart will come in handy. It'll make another appearance in the video a little bit later on, but I wanted to sort of talk a little bit about that and clarify that for you. So Ka and Kb are one way to describe the strength of an acid. And an alternative system, which we do use, maybe not quite as frequently as Kas and Kbs though, but I do want you to be familiar with it, and it may pop up in some of your homework, is very similar to pH, right? Well, pH is a different way to describe how much H3O plus is in an aqueous solution, right? Instead of having to use the language of molarity, we put things on this scale that runs roughly from 1 to 14. Well, it turns out we can apply that P scale to the Kas and Kbs as well. So we can talk about the pKa of an acid. That would simply be the negative log of the Ka of the acid, or the pKb of a base, which would be the negative log of the Kb of the base. Now the P scales invert or flip around your understanding, right? On the H3O scale, for example, the more H3O you have, meaning the more acidic the solution is, when you take the P value, the pH, it's lower on the scale. So in the case of Kas, strong acids, which have large Kas, lead to low pKa values, right? So your strongest acids tend to have pKa's of like 1, 2, 3 maybe, okay? 1, 2, or 3. Whereas your weak substances, your weak acids, again, these would have small Ka's now, 10 to the negative 5, 10 to the negative 8. That is going to lead to much higher pKa values, all right? So like above 4, for example. And of course, that would adapt for the pKb's as well, all right? On the pKb scale, the low pKb's are the strongest bases, and the high pKb's are the weakest bases. Now, just a second ago, I had described a relationship between Ka and Kb, right? And now we've just taken the negative log of them, so you can bet that there is a connection between these two. It turns out that for any conjugate acid-base pair, the pKa of the acid plus the pKb of the base equals 14. Again, just like pH plus pOH equals 14, right? And that's because these are both connected, in the one case H3O and OH, and in this new case Ka and Kb, they're both connected by the water ionization constant. All right? So this just gives us another way to find the K value or the pK value for acids and bases. And we'll see some of this in some of the examples that I'll work out in subsequent videos for you, subsequent presentations for you. All right? Do keep in mind that the way to undo any P value, so for example, if you wanted to find the Ka of an acid to use in an equilibrium problem, for example, you would need to take 10 to the negative pKa to basically invert or do the inverse of this function up here. Okay? All right. So you'll want to keep your Ka chart handy. Again, these are Kas, not pKas. All right? The actual ionization constants, and you'll use that quite a bit. Now, what if you should encounter an acid or a base that's not on your Ka chart, but perhaps is similar or maybe looks like some other acids or bases that are on your Ka charts? Well, it turns out that many acids, they demonstrate a trend in strength, meaning Ka, that depends on the size of the anion produced when the acid donates H plus, right? So again, HA is reacting with water. HA is our generic version of an acid. It produces H3O plus and A minus. So what I'm talking about here is this. So if you had a family of acids that all seemed similar, and you only knew one or two of the Ka values, you could roughly figure out what the other ones were. For example, HF, HCl, HBr, and HI. These first two acids are on our Ka chart, and you could look up HF and find a number for it. It's fairly small. And then HCl is near the top of your chart, and it has a rather large Ka. It's the it's the word large, meaning it's complete. Fluorine is a small ion. If I drew it next, relatively next up, chlorine would be that big. Bromine would be even bigger, and iodine would be even bigger. As the size increases, you see, from fluorine to chlorine to bromine to iodine, it's getting easier and easier for the same size little hydrogen to be pulled away from this larger volume that we have. The easier it is to pull the hydrogen away, the more this thing is acidic, right? The stronger, in other words, it is. The easier we can take away the hydrogen from the other part, then the more likely it is to be an acid, to be a donor. And so as size increases, the Ka generally tends to increase as well. Okay? That's our trend. As the anion size increases, so does the Ka. This plays itself out in other places as well. Another important family that demonstrates this is the acid that I had up for our conjugate pair demonstration, HClO, HClO2, HClO3, and HClO4. Right? In each of these cases, we have the chlorine constant there. All right? But what we're doing is adding more oxygens. And so one way to imagine what's happening here is that, again, the anion is getting larger and larger and larger as you go from HClO to HClO4, thus making it easier to remove that one little hydrogen from that much larger structure. Another way to phrase this is to think that it's easier for that one extra electron that we keep from the hydrogen atom, right? We take this hydrogen atom and this thing keeps the electron and the proton goes away, right? So it's easier to fit that extra electron into larger volumes and therefore easier to get rid of the proton. The more easily we get rid of the proton, the more acidic we are, the larger our Ka is. But again, the easy way to remember that is really it tracks with the size of the anion that we have. Okay? All right. Now these anions that we've produced, right? And if you look at the Ka chart, you will start to see, in particular on the base side, but some on the acid side as well, you'll start to see that there are lots of things that are ions that are behaving as acids and bases. The trouble is, if I want to use some of these ions to create an acid-base reaction, I cannot just go get a container of one of those ions. For example, if I wanted to get the ClO minus that we had earlier in a reaction that I had up here a few minutes ago, I can't get a jar or container of ClO minus ion. All right. It just doesn't exist. It needs to have a counter ion to balance its negative charge. It could be hydrogen, and in that case that would be hypochlorous acid that we would have, all right? But it also could be a metal or some other ion that counters that charge. In the case of it being a metal, we would then have a salts, right? So salts, remember, are just ionic compounds. Salts often contain ions that are able to act as acids or bases when added to water. Right? Any generic salt, let's say XY, right? The average salt, XY, when we put it into water, dissociates into its two ions, X plus and Y minus. Right? If either one of these ions now is on our Ka chart, it actually is going to act as an acid and potentially then react with water. For example, if we had sodium NaClO solid and put it into water, that would produce sodium ions and hypochlorite ions. Well, we've already seen that these hypochlorite ions can then in turn react with the very water that helped pull them apart from sodium ions. That would create OH minus and some HClO, because hypochlorite is a base. It has a measurable Kb that we can see on our Ka-Kb chart, all right? And we've already seen that it acts as a base. That's how I know that it's going to produce this OH. This OH then in turn, remember, is going to take the water up here that was originally balanced for its H plus and OH minus, and after this reaction, it's now going to have a smaller quantity of hydronium, or H plus, and a much larger concentration of OH minus. Thus, it's going to be basic overall. And I would say that sodium hypochlorite is a basic salt. And I would need to be worried when I put it into a solution if I did not want the pH to change of that solution. Okay. Sodium hypochlorite is bleach. You might remember that from Chemistry 1 here at YCP. We titrated it to determine the amount of sodium hypochlorite in a regular old household bleach. Okay. So how does this all play out? Well, for any salt that would dissociate, generic XY over here, if one ion of the salt has a numerical Ka, okay, the ion will react with water to form H3O plus. And we would say that the salt is acidic because this ion has led to the creation of H3O plus, which is an acid. On the other hand, if an ion of the salt has a numerical value of Kb, or 4 Kb, the ion will react with water to form OH minus, and such a salt would be basic, just like sodium hypochlorite over here. There's a third option. If neither ion has a numerical Ka or Kb, the salt is neutral. And so they'll get no reaction. If neither ion is able to react with water, it'll just leave water alone Neutral, the pH would be 7, right? So ideally we'd leave water at 7. And then there's one more possibility that we'll take up. There are actually two more, but one's kind of advanced that we'll ignore. But there are some ions, if you look at this Ka-Kb chart and some that we've talked about already this chapter, there are some chemicals that can behave as both acids and bases. So if an ion has both a Ka and Kb, it will follow the larger value. This is a little tricky. Actually, both things are going to occur. Some of the ions would be acting as acids and some will act as bases, but the net result will match the larger of those two values, right? So if you had 1,000,000 molecules of something and maybe 20% were acting like acids, but 80% were acting like bases, you're going to be seeing a lot more OH minus produced, and then you know that salt in the net result would be a base. Okay? Let me show you how this works. Do some examples. Leave our guidelines down here. All right, let's figure out the nature of these four salts. K2CO3, NH4Br, NaCl, and MgHSO3 2. So your first task when you are presented a salt, all right, number one is to recognize that it's a salt. That's a chemistry 1 topic. Salts generally feature a metal and a non-metal, right? And we can recognize that using the periodic table, using the line that divides metals from non-metals. So we have something from each side of that. Or the other thing is that they contain a polyatomic ion, like this one here contains the carbonate ion or the ammonium ion. So continuing to recognize our polyatomic ions, keyword, ions. So they're part of ionic compounds. So after we recognize that something's an ionic compound, we want to figure out where is it going to cleave? Where is it going to divide? Just like X, Y that I had up a couple of minutes ago is going to split into X and Y respectively, we need to figure out where these salts are going to divide. So K2CO3 would divide between the K and the CO3. NH4Br, between the NH and the 4, and the Br. NaCl will produce sodium and chlorine, and then magnesium hydrogen sulfite will produce magnesium and hydrogen sulfite. Okay. Now you need to look for your two respective ions on your Ka chart. All right. So on the Ka chart, I can find no evidence of the potassium ion. All right, you can look, it's a big list, right? But you can look up and down and you will not find potassium ions on it. That's pretty much going to be true for everything in groups 1 and 2. Potassium, sodium, lithium, calcium, magnesium, beryllium, right? Those things don't act as either acids or bases. So they do not have what I've been saying, a numerical value. You're not going to find a number for them. Okay? On the other hand, you do find that CO3 has a Kb. So CO3 minus will be able to do the same reaction that we had up a minute ago of hypochlorite with water. It's going to react with water. That negative charge is going to accept hydrogens from the water, and that makes CO3 minus a base. And as a result, this entire salt would be considered basic. All right? Our NH4Br will split into NH4 plus and Br minus. Again, looking at our Ka chart, you'll find no evidence of the bromide ion. You will find that NH4 plus has a Ka, and it's acidic. That makes the entire salt acidic. Okay? So you just need to divide and conquer, so to speak. NaCl, Na plus, Cl minus. Just like with the potassium, you won't find Na on there. Now you will find chlorine, but it's at the very top on the Kb side, right? Negative charges, no hydrogens. We better be looking at the base side of our Ka-Kb chart, right? The lack of a hydrogen is really a dead giveaway that this thing can't be an acid, right? So we're looking on the base side. But the fact that it says very small, is very small a number? No. So that's my test here. Very small is telling us chlorine is such a poor base that it's not actually going to act like a base. Chlorine comes from hydrochloric acid, HCl, doing its job acting like an acid. And HCl is such a good acid that it never wants to turn backwards into HCl. It always wants to drive that H over to something else. So this chlorine then is also going to be ignored. And the net result here is that this NaCl is a neutral salt. If you put salt into water, its pH should remain constant, whatever it was before you put it in. If that was pure water, the pH would stay at 7. Okay. All right, and then the last one, we would have the magnesium ion, Mg2+, and then we would have the HSO3- ion. Well, quickly I can tell you we're going to ignore the magnesium yet again, just like the other metals. It's been ignored. The HSO3 is a little bit trickier though. HSO3, I can find it on my Ka-Kb chart. HSO3 has a Ka equal to 6.4 times 10 to the minus 8. But it turns out that it also has a Kb. Kb equal to 6.2 times 10 to the minus 13. Now these two values are not side by side, so I want you to make sure you can find them on your Ka-Kb chart right now. HSO3 as an acid is right here. It's about halfway down or so. But HSO3 behaving as a base is all the way up here on the chart. So these are in two different places. HSO3, we're not comparing HSO3 to its conjugate. That would be SO3 2-. We want to compare HSO3, its desire to act like a base, to its own desire to act like an acid. And that's what these two different numbers, not side by side, would be. Now we can see that the larger of these two is the acidic identity. As a result, MgHSO3 is going to be an acidic salt. This is 5 powers of 10 difference. So that's 10, 100, 1,000, 10,000, 100,000 times more. So for every one that acts like a base, roughly, 100,000 are going to act like an acid. I hope that makes it easy to understand then that HSO3 is an acid, all right, when it shows up in a salt. Okay. All right. So now when salts show up, that's really the first job, is to figure out if they're acidic or if they're basic. So at this point now, we've really covered all of the fundamental acid-base sort of foundation information, and we're ready to get back to doing problems like we did in our previous equilibrium chapter. There's really just two main types of problems, to be honest. The same two types that we did back in the previous chapter. Sometimes we're asked to find the equilibrium constant. Now, it might not be called an equilibrium constant. It might be called the Ka. Find the Ka. But that's exactly the same thing, right? A Ka is an equilibrium constant. Or, the problem might be clever, and it might say, find the pKa. Well, that's just the Ka, and then you take the negative log, right? So we'll still be finding the equilibrium constant. That's one version of our answer. Problem, I should say. The other types of problem that we did were find the equilibrium conditions from the equilibrium constant. The way these will be spun in this new chapter about acids and bases, though, will be particularly to find the H3O concentration and not express it as a concentration, but rather express it as a pH value, right? So you'll see a lot of problems. Find the pH of blank, of this solution, right? And that really is, you have to turn that in your head. Oh, that means at equilibrium, what is the H3O concentration? That problem, when you state it that way, is just like the problems that we did in our previous equilibrium chapter. Okay? What makes our acid-base chemistry problems a little bit more challenging is the fact that we have so many different things. We have materials that act like acids, materials that act like bases, and we have salts now, which can act as either acids or bases. So our first job, before we write any reactions and do anything, is to think about what the species is. This is a new responsibility that's being given to you. In the previous chapter, you were just given the reactions. Now that we know how acids and bases behave, you're going to be expected to be able to write those reactions on your own. So here are my tips for how to set up and solve acid-base equilibria. Okay. In particular, this is going to work well for when you're asked to find the pH of a solution, but it could work for finding the Ka of a solution as well. You want to first ask yourself the question, what is the species? And by that I mean, is it an acid or is it a base? Pretty much everything will fall into that category. Even if it's a salt, as we just talked about, if something is a salt and it dissociates, there's a good chance that one of those two pieces is going to act as an acid or as a base. All right? So once you decide if it's an acid or a base, you want to decide how, or now you want to say how will it react with water? Because that's going to be the other reactant, even though it might not be mentioned. Remember, anytime pH is asked for, you have to be in aqueous solution because the pH scale is built on water, the two parts of water. So this is part of the vocabulary of acid-base chemistry, that water is always there in the Bronsted-Lowry system. Okay, so how will it react with water? There's only two possibilities, right? It's going to either produce some H3O plus if it's an acid, or it's going to produce OH minus. So you need to be able to write a reaction that shows one of these two things being formed. You can use the generic patterns that I've shown you in class, HA plus water, or B for a base plus water. Okay? So once you've written the reaction, now you want to write the KEQ expression, which would really be Ka or Kb expression. This is going to tie together the various components of the reaction, all right? And then from there, it should start to look really familiar. You will set up a reaction table. Okay? If it's a table where you're given some initial information and given some final information, or you have to add one of those variables to represent how the system changes, you'll start to see those are going to look very familiar to what we did in our previous chapter. So you'll set up your reaction table and solve for the unknown part. That unknown part can really vary. It could be a concentration at equilibrium. It could be how much reaction has occurred. There's a couple of different ways to do that. And then at the tail end, what I really like about acid-base chemistry is we can check our answer. So now, does the answer make sense? And when I say makes sense, for the identity of the species. If you have decided that this species is an acid and you are calculating the pH, remember that means that the pH needs to be below 7. If you identify that a salt is basic because of one of its ions, and you're asked to find the pH, then that pH needs to be above 7. If you're asked to find the Ka of a weak acid, weak acids we've talked about have small Kas. You need to get 10 to the negative 4, 10 to the negative 7, not big numbers, right? This is closing that loop, being critical of your own work, and being willing to find a mistake if it did exist. But there are plenty of good ways to check your work in acid-base chemistry. So I'm going to stop here, and I'm going to then lead you off into the next video, which will show you how to set up and solve a variety of equilibrium problems. If you have any questions, always feel free to reach out to me and contact me, and I'll be happy to elaborate a little further when the next time I can. Otherwise, I wish you the best. Hope you're having a good day. And as always, thanks for tuning in and using our channel to help you learn your chemistry.